Okay, on page 14, we've got a golf ball that's hit from the ground towards a long flat hill that is 10 meters tall. And so, just like we saw last time with the backboard, they want to know if it's going to make it onto the hill. And so notice I drew 3 different patterns here as options. How do we know if it makes it on the hill or not? What's the physics variable that we have to solve for? Same as what we solved for with the tennis ball problem. Do you remember? We do need time, but that's not what we'll use our final answer for. What's going to be that final solve to answer the yes or no question? Does it make it onto the hill? What did we solve for with our tennis ball in order to answer that question? Right, the displacement in the y at that point. And so if we look to make it onto the hill, later they tell us it's 40 meters away. And so we'll end up doing like we did last time, solving for the time to travel 40 meters. But then our final answer for part A is going to be solve for that final y position. Okay, they tell us that the hill is 10 meters tall. And so we'll compare it to that 10, just like we compared it with the backboard last time. Everybody got our game plan? Okay, so we hit the golf ball from the ground towards a long flat hill. It's 10 meters tall. If the ball leaves the club, so it's not, we don't care about the hit, we care about after the hit, that's when it becomes a projectile. And it's going to leave at a velocity of 30 meters per second at a 40-degree angle. Now that's a different 40 than the 40 meters. Sorry, it's the same number, but it's a different physics. And it tells us the hill is a horizontal distance of 40 meters from where it's hit. And so, yeah, we need that final vertical position, but just like the golf ball or the tennis ball one, we need time first. And so the first thing we're going to do is solve for time in the horizontal, because we do know the horizontal displacement to the hill. Notice part A is just caring about to the hill, where B, C, and D are talking about the hole. What else do we know horizontally? What about 30 meters per second? Is that our horizontal velocity? 30 meters per second. No, that's the one at an angle. It's not horizontal or vertical. And so we need to come in here and solve for the horizontal component, Vx, and VIY. And here's a helpful tip. Anytime your object, your projectile is launched at an angle, make that your first thing. Your chances are you're going to need both components. So just go on and solve for Vx and VIY. Now, how do we find those? If you look at it as a triangle, the 30 meters per second is the hypotenuse. Vx is adjacent. And so what trig function are we going to use to find Vx? Adjacent, hypotenuse, cosine. And so if you remember last time, I kind of gave you some shortcut. It was already solved for the component. So it's our hypotenuse times the function. And so for horizontal, and again, I'm going to highlight this. It's very, very common. I would say most of your projectile problems are going to be with the horizontal. And so 90% or a little more, you're going to use cosine to find that horizontal component, okay? And we'll use sine to find the vertical. So again, these, my hope is that you use them so much in your practice that come exam time next week, right? You don't get them mixed up or such. Okay, you can always draw your triangle though to see which one to use. And so for Vx, they said 30 was our hypotenuse, was our actual speed, and then our angle is 40 degrees. Now, before you punch it in, make sure you're in what mode, degree. So if you have a calculator, check that mode. If no one at your table has a calculator, someone go get one. We're going to have more than 1 or 2 people calculate. So you punch it in just like you see it. What is 30 times cosine 40? 22.98. Now, do we round that? Honestly, if I were working, I'd probably round it. But if you're like, no, it's not a final answer, I don't want to round yet, I'll give you that, because that's something else I say, don't round too early. So if you can stand it, 22.98. What about the vertical? 30 times sine 40. What do we get for the initial vertical velocity component? 19.28. So we're done with 30 meters per second. Done, 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 done. This is not going to be a symmetrical problem. And so even if they asked for impact speed later on, the impact speed that it makes going into the hole, it's not going to be 30, right? Will it be less than or greater than 30 when it goes into the hole later? Less than or greater than 30? Why less than? Right, and so that 30 meters per second, depending on what peak you draw it on, it's going to decrease overall as it goes up, and then it's going to increase as it comes down. But since you end higher, you don't come down as much. You're not going to speed up as much. So yeah, eventually when we land in the hole, it should be less than 30. Okay, so with that, now we know the horizontal velocity. Is this enough to find time in the horizontal? What equation do we use in the horizontal? The second one. So I'm going to put it in horizontal displacement terms. Now, since it's our first one today, I'm going to keep the 1/2 AT squared. But what's true about horizontal acceleration? Right, it's 0, and so it's going to go away. So most times in the horizontal, I just write that first part of the second equation, okay? And so now we know 40 meters equals 22.98. Now we can find the time in the horizontal. And so as you punch it in, just a friendly reminder, time is the one physics variable that's equal in both dimensions. It is standard 2D kinematics, projectiles, to have to find time in one direction and then use it in the other direction, okay? Most of our problems here are not just a one step and done, okay? All right, what do we get? 1.74 sounds familiar. Not our final answer. And so then, now that we know the time, just like our tennis ball, we can go solve for that final vertical position. Because that's what we need to answer the question, does it make it on the hill? And so, what do we know vertically? Gravity. I'm going with standard sign convention, right? There's no reason not to. What else do we know vertically? Right, we found that initial velocity component and got 19.28. What else do we know? We know time carries over from the horizontal, so the time is the same. Is this enough? Usually when you start getting 3 numbers, you can start, is this enough? So what equation can we use to find that final vertical position? Second again, because we don't know that final velocity. And so YF, I'll put it in terms of position. By the way, we've been using our derived equations for about a month. For those of you who have been writing the original equation down like I have, do we have them almost memorized yet, just out of muscle memory? You don't have to memorize them. They're on the formula chart. You get it from now on, but maybe you have them, memorized. And so it's already solved for final. Initial vertical position, it starts on the ground. And so we'll call that 0. And so 19.28 times 1.74 seconds plus half of -10. And then the same 1.74 seconds, but on this one, don't forget to square. So calculate it out. Now the answer we get is not our final answer. They asked us, will it make it on the hill? So we have to compare the answer we get to our 10-meter hill height. Yes, that sounds familiar. So 18.4 meters is the instantaneous vertical position at that time. So does it make it over the 10-meter hill? So yes, it does. It goes over the hill. Over, I don't know what I was writing. Over the hill by 8.4 meters. Okay, so you subtract the height of the hill. It's going to clear it 8.4 meters. Questions on A? Okay. Well, let's switch now. B, C, and D all talk about, well, what if it hits the hole, which is on the hill? So now we know the vertical displacement when it lands in the hole. We know it's going to have 10 meters in terms of vertical displacement. But now how far is the hole from the edge of the hill? Not from the golf ball where it was hit. So let me go back to our picture here. They want this distance, right? How far from the edge of the hill is the hole? Well, we know that the full distance in the horizontal direction is what we call range, right? Now it's not symmetrical, but we need to find the full range of the golf ball. And they gave us what I'm going to call D1, 40 meters. How can we find D2? Someone say the S word. Don't say slope. How do we find D2 after we know the full range? We subtract the 40 meters, right? And so we know that D1, which is our 40 meters, plus that second distance that we're looking for is going to equal the total range. And so the physics I got to do first, we'll find the total range. We still don't know that. And so this summative type equation we'll do at the end, okay? So next goal, what is the range? Well, it's horizontal distance. What do we know horizontally? By the way, did they mention changing the velocity or the angle? No. So we can assume it's the same VI and angle. And because of that, we can use the same components. And so Vx earlier was that 22.98. So that's going to be the same. What about time? Is it still 1.74? What was that the time of? To go to the hole? Right, that's just to cover D1. Well, can we just multiply by 2? 1.74 times 2? There's a couple wrong reasons for that, right? We don't know if the peak happened right there. Plus, it's not symmetrical today. We have an uneven, right? Asymmetrical. And so we don't know the time, ... So again, classic 2D projectile. If you don't know time in the horizontal, pause and do what? Solve for it in the vertical. Okay, so what do we know vertically? Well, the initial vertical velocity is still that same 19.28. We still have gravity, standard sign convention, right? And now that we know it lands in the hole, don't we know the vertical displacement? Or you could do it in terms of position. The initial vertical position starts on the ground. Final lands in the hole, which is what height? Up 10. And if you wanted to, you could go on and say final minus initial, 10 minus 0. We get a positive 10. And that hopefully makes sense because under standard sign convention, when your ball or object ends higher than it started, that's a positive displacement, right? Okay, is this enough to find time? We got 3-ish numbers. Start looking at your equations. Can we solve for time? Yes, which equation? Second one. And so I'm going to go in and put it in displacement terms since we found it. And so equals VIYT plus 1/2 AT squared. And so we know positive 10. VIY was that 19.28. There's time that I'm looking for. Plus half of negative 10. By the way, it's okay if you go in and say -5. Okay, you'll even see, like if you watch supplemental tutorial videos or such, a lot of physics people will go straight for the -5. Okay. All right, so how do I solve for time? Oh, there's that Q word, right? So remember, if nothing zeroes out, and I'm using that second equation to solve for time, it's t and t squared. And if you're thinking back to a couple classes ago when we divided both sides by t and it simplified out, that was when it was symmetrical and delta y equaled 0. Well, that's not the case today. Nothing zeroes out. So if you love quadratics, sing your song, do your calculator thing, and go for the time. Or who remembers the workaround? We went over this last week. Before I find time, what's that other unknown variable? What else don't we know? We chose that equation because we didn't know final velocity. But what if we find final velocity first? And so yes, it is a two-step type of workaround. And you may be like, oh, that's twice the work. Okay. Well, if you don't know quadratic, yeah. If you don't know quadratic and they don't give it to you on the formula chart, and so it's easier to use the two that are on there, right? But take your pick. These are two different methods to getting it, all right? And so how do I find the final velocity? Question? Oh, are you sure? Okay. How do I find the final velocity without time? Which equation? Third. And so that VF squared equals VI squared. Keep them all vertical. And so it's somewhat solved for final. We'll square root at the end. And we have 19.28 squared plus 2 times -10. And then your vertical displacement is positive. So notice you'll be subtracting 200 from whatever that 19.28 squared is. So punch it in and then give me the answer after you do the final square root. 19.28 squared minus 200, and then square root. And by the way, before you say the number, so for this question's for those not calculating. Ooh, should it be equal to 19.28, greater than or less than? Why less than? Right, so again, we don't come down as far as we went up. And so we haven't quite had a chance to speed back up to the initial velocity. And so that it should be a smaller number than 19.28. Now, what do we get? 13.1. 13.1 meters per second. But wait, there's more. Switching colors for emphasis. When it lands in the hole, it's going what vertical direction? Chances are. When it lands in the hole, it had went up, 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 and then came down, right? The calculator, when you square rooted, gave you a positive number. But here's where you need to be careful, okay? It's positive or negative. Which one is it? It should be negative because when you go land in the hole, it's moving downward. Okay, so it should be negative. And you're like, she keeps making a big deal of this, but it never makes a difference. Actually, here it will. Then we're going to use that final velocity to solve for time with the first equation. And not that you physically have to put it in, but at least mentally, let's start with a positive 13. What if I didn't recognize it's negative? Notice you'll have to subtract 19 from 13. So let's just call that negative 6-ish. And you divide by negative 10-ish, we're going to get a positive time of 0.6-ish. But that's wrong, okay? But when you make it a negative 13, again, highlight for emphasis. Now, rather than taking the difference of those two numbers, we're summing 13 and 19, right? And so, you know, rounding a little bit, it's around negative, what, 30-ish? Oh, 33-ish, 32-ish. Divided by negative 10, we're going to get a number way different than 0.6-ish, right? What do we get? Correct time is 3.23 seconds. Okay, so when you do the workaround, use the other two equations, find final velocity first. When you square root, consider, do I want the up or down direction for what they're asking? And then use the first equation to find time. Did anyone do quadratic? Just for comparison, what'd you get? .62, and then what was your other one? Okay, and so what the 0.6, that was the first time it was at a height of 10 meters, right? So that's what we were mentally calculating by making that a positive 13. Okay, and so that's the first time on the way up 10 meters, but to land in the hole, it's got to be that second time we're at the 10 meters. But you should get same thing. Good deal? And that's not even our final answer. Goodness gracious. Why did we do all that? Well, we needed the time for the horizontal. And so now we know 3.23 seconds. Now, how do I find that big total range? Right. Our equation is horizontal velocity times that time. And so multiply those two numbers together. I'm running out of room. But what's 3.23 times 22.98 or 23? Point what? 2. And that's not my final answer. But one more step. What do we do to get our final answer? Say again. Subtract 40. And so that D2 from the edge of the cliff to the hole that they asked for, I got to subtract that first distance given, 40. And so we should get 34.2 meters. That's our final answer, okay? Questions on B? All right, well, lucky for us, C and D are still at the hole, so everything we just did in B, we can continue using. They didn't change things up for a third time. And so now C says, how fast was the ball going when it landed in the hole? So I kind of alluded to that. It's going to land in the hole going a down and forward direction. And so this is their way of asking for impact speed. And then part D, what angle does it enter the hole? And so to solve for an angled vector, we need two other pieces. We need that final vertical, and we need a horizontal component. Well, lucky for us, all that hard work solving for the 2 steps compared to the quadratic is going to pay off. We already know the final vertical velocity, right? That was that negative 13.1. And so we know this is negative 13.1. Horizontal velocity is constant, so that's the 22.98, right? And if I know 2 sides and they're perpendicular to each other, how do I find the hypotenuse? Pythagorean theorem, which AP does give you. And whether you use that negative or not, hopefully you see that, you know, speed or anytime you do Pythagorean, those negative components are going to square away. Save a keystroke, y'all, because if you type it in with good intentions, but without parentheses, you'll get the wrong answer, okay? And so I would not even put negative in, just 13.1 squared plus that 22.98 squared equals that impact speed squared. And so go on and do your squares, do your addition, square root, should be bigger than 23. Yeah, 0.45, and then meters per second. So that's the hypotenuse. Remember, we launched it at 30 meters per second and said that it wouldn't be going as fast when it landed in the hole, right? So that's a true statement. We got 26-ish. It's not going as fast. Good. Okay. Well, now that I know all 3 sides of the triangle, can we solve for the angle that it makes with the ground? And I'm choosing the ground just because a lot of these projectile problems, you choose it with your nearest surface. The ball lands on the ground. The ground is horizontal. And so it's the angle with the horizontal. And so, true story, you can use sine, cosine, tan. What do y'all want to do today? Anybody can say. Which one? Tan. And by the way, as you read through your textbook, hint, hint, wink, wink, right? Or thumb through or click through and look at the pictures. Tan is what the textbooks use because we don't know if our hypotenuse is correct yet. And so I personally like the more descriptive. Formula chart uses ABC. I like the ones that are more descriptive in what part of the triangle they are. And so based on where my angle is, opposite is the VFY, adjacent is the X. Now tan, just magnitude it, okay? It confuses the quadrants. So I'm just gonna 13.1 over 22.98. And when you get that, so, you know, 0.4 something, that's equal to tan theta. How am I gonna solve for theta? arctan, inverse tan. And so you can either put your two numbers in at that point, or maybe you already know your 0.4-ish number. And so again, got to be in degree mode. Second tan, put your numbers in. Let me know what angle you get. Now, before you say it, we launch this thing at 40 degrees. It goes up, but it doesn't come down the same amount. So should our angle be equal to 40 degrees, less than, or greater than 40? Should be less than 40. And so it just gives you an idea, okay? If you get a number less than 40, chances are you might have done it right. What do we get? 29.16. Yeah, I'm gonna call that 30. Usually with angles, you round to the nearest half angle. And so 29 point, what'd you say? 6.8, yeah, you can round that one up, 30 degrees. So it's 30 degrees above the ground. Good, nothing new there. Okay, actually, I don't know if I said it earlier, we're done with new stuff. It's just practice, a variety now, and do lab. Okay, let's move on to page 15. 15 has one problem. We're doing a football example now. So there's no picture, I'm gonna draw one. And so it says a football is kicked from the ground at an angle of 30 degrees above the horizontal. And it lands on the ground. Wait a second. Ooh, ground to ground. Everybody do your happy dance. This is symmetrical. Yay, right? Okay. So it lands on the ground 50 meters from where it was kicked. What was its initial speed? Now they're giving you a hint here. Use the variable VI for when you get your setup equations, okay? So you'll see what all that means here in a second. And so get a little picture here, oops. And so we got our football, or whatever it is. Again, we don't care about the kick, we care about after the kick. So we're gonna just say it leaves the ground at some VI, that's what we're looking for. And they do tell us 30 degrees. And it's gonna land on the ground, so we get to do the symmetry. So it goes up, 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 and down. It's gonna land at what impact speed? I'm not looking for a number, but what do we know about the impact speed here if it's ground to ground? It's equal to whatever the initial launch speed or kick speed was, right? What angle does it land with the ground? 30. So that symmetry helps tell us things, right? Some other things that it tells us, if we look at the peak where it's only moving in the horizontal, remember the V peak in the vertical is 0, right? And symmetry, if we know time up, it equals time down. Now that's not necessarily X, Y, it's just period. The time up is equal to time down. So we could, just like we derived the Tiger Woods equation last time, right? Okay. So what was the initial speed? So earlier I'd said, make it your first first step, take that initial velocity and find the components. Well, we can't fully do that here, but we can kind of get it set up. Long story short, y'all, we're gonna have two variables along the way, and eventually one will go away and we'll solve for VI, okay? But for right now, just keep that VI. And so Vx is VI times cosine 30. And VIY is VI sine 30. And we could actually put some other numbers, unless you want to carry through cosine and sine, or punch it in. What's cosine 30? It's a decimal number. What do we get? 8.7. times VI. So that's what we're going to use for the time being. And then sine 30 is 1/2, 0.5. So that's about all we can do with our initial velocity. And no, we can't get an answer yet, okay? So typically, imagine we did have a number, right? What are some of the things that we've done? We found time in one axis, used it in another axis, right? Well, they also did give me one more bit. They said that 50 meters is where it lands. What did they just give us? What is 50 meters? Range. And so if we think about horizontal, we know that the range, 50 meters, is equal to that horizontal velocity, which is 0.87 VI, times time. And again, that's about all we can do with it at that point. So pause in the horizontal. Let's go vertical. What do we know vertically? Well, it's ground to ground. What's delta Y? 0. Okay, it's symmetrical. What else do we know vertically? Well, the initial vertical velocity was that 0.87 times VI. We know gravity. Thank you, sorry. And what else do we know? There is one more thing. If you look at the symmetry, what would the final vertical velocity be? The vertical component. Not 0, not final when it hits the ground. The peak would, right? Which we could go that route. But the final vertical velocity, remember we talked about the symmetry, right? So the angle that it leaves the ground and hits the ground is the same. The hypotenuse is the same. So our vertical component is the same magnitude, but now it's moving what direction? Negative. So I could say that the final vertical velocity is a negative 0.87 VI. Now you don't actually have to recognize that. I'm going to show you that we can actually solve time two different ways here. The first way is without that final vertical velocity. Remember, just like last week, when you use this equation and there's symmetry, that delta Y zeroes out. And so here's where we can, 0 equals 0.87 VI times time plus 1/2 of -10 times time squared. So I can add 5t squared to the other side because this is -5. So this is repeat what we did last week. No quadratic, because remember, delta Y zeroed out. You can divide both sides by t. And so at this point, we have 5t equals 0.87 times VI. Still two unknowns. Now, I just pointed out the final velocity because maybe you don't see the second equation as an option. Maybe you see the first one. You're like, I want to use the first equation to find time. So when you have symmetry, I get negative 0.87 VI equals a positive 0.87 VI plus -10 times time. Notice what's going to happen when you put those VI's together. Combine like terms. Does it cancel out? No. You end up, it's a double, right? And so we'd get a negative 1.74. Divide both sides. What do we get for time? A positive 0.174 VI. Now that may not look like the same thing, but let's go on and make sure it is. 0.87 divided by 5, someone punch that in. Don't just tell me it's the same. What's 0.87 divided by 5? Say again. 0.17. Was there a third digit? 4. Okay, so it comes out exactly the same. Okay, and so these are two different ways to find time in the vertical for symmetrical problems. So you can use the first equation if you recognize the negative final velocity is equal to the initial velocity vector, or you can do that delta y equals 0 with the second equation. And so you may be wondering, well, gosh, how in the world are we supposed to figure this out? Well, notice both equations, horizontal and vertical, they each have the same two unknowns. So we ultimately want to say VI equals this number. That's my final answer, right? And so I've got the vertical one solved for time. Can't I take this equivalence and plug it in right there? So if you have two unknowns, just hold on to them. You should be able to use two equations and substitute in. And so 50 equals 0.87 VI times 0.174 VI. Will you go pull the door, please? Put the little door stop. And so here, grab your calculator. We're almost there. It's so close. VI times VI, we'll get VI squared. That's okay. What's 0.87 times 0.174? 0.87 times 0.174. .15, and it still equals 50 there. So how are we going to solve for VI? Divide both sides by 0.15. And this will equal VI squared. This is going to be a bigger number. It's okay. Wait, hold on, 18? 50 divided by 0.15? Oh, not yet, not yet. Sorry. 333.3? 33. So it's all repeating there? Okay. So that equals VI squared. Now, final step, drum roll, please. Square root both sides, right? And so final answer for part A, VI equals, now tell me, 18.26. What'd you get? You got the same thing? I remember a different number from another class. Okay, the 1.7 is okay. I was expecting the number 24. That's what we got in second period. Now, I don't have access to the key, so I don't with the server issue stuff. So, you know, 24 could be wrong as well. That's why I really want multiple people calculating. I'm just looking for, did we mix something up? Did I? Sure enough. Good catch, good catch. So let's grade Miss Earhart. Where did she go wrong? I plugged in the horizontal velocity for the vertical. You didn't notice that 10 minutes ago and keep your mouth shut, right? Okay. So yeah, if you ever see me make that, you know, by the way, that's the #1 student mistake on exams. You mix, you put a horizontal information in the vertical. So let's correct this real quick. Different color, what can we use? So it should be 0.5 VI, which would make the final velocity -0.5 VI. which would change this right here. And so now, what's 0.5 divided by 5? 0.1. And I'm assuming that that one will come out the same. And so to sum my 0.5 and 0.5, it would be negative 1.0 divided by 10, which would be 0.1. So we still get equivalence. Oops. And then when we bring it over here, this should be 0.1. And so what's 0.87 times 0.1? It would be I've already forgot what I said. It'd be 0.087, right? 0.087 times VI squared. And so now what's 50 divided by 0.087, and then go ahead and do square root. Okay, so now I feel better. 23.96, in other words, 24 meters per second. And so that's our answer from A. Good deal. Now B is going to go quicker. How long is it in the air? We know a proportion. We know that 0.1, T equals 0.1 times VI, but now that I know 24, can't I go in and plug it in? And so T equals 0.1 times VI. And so 0.1 times 24 would be 2.4 seconds. So that one goes quicker now. See, how high did it go? Remember, this one's symmetrical. So what can we do? That's a, how high did it go? This is a peak vertical position, right? So if it's symmetrical, how do I find the time up? I know the whole thing takes 2.4 seconds. If it's symmetrical, time up equals time down. Added together, they got to equal 2.4. So how do I find just the time up? Divide by 2. It's our total time divided by 2. So 2.4 divided by 2. So the time we're going to use is 1.2. Now, what else do we know? We're looking for that final vertical position. Vertically, we still, now, can we find the vertical initial component of the velocity? Yeah, earlier we said that the vertical was 0.5 times the initial velocity. Now that we know the initial velocity, it's half of 24. And I know the time, 1.2, and I know gravity. Is this enough to find the vertical final position at the peak? By the way, we also know one more vertical thing. What's your vertical velocity instantaneous at that moment when it's at the peak? 0. So we know the peak vertical, and you can call it final if you start at the ground. So with all that, which equation? I can use the second one. And true story, since we know the final velocity, you could use the third one, okay? To save a little time though, I'll just use that second one since it's already solved for YF. And so we're starting on the ground. It was unspoken that that was 0 meters, right? And so we know 12 meters per second times 1.2 seconds plus half a negative 10 times 1.2, don't forget to square. So plug this in. And let me know what you get. Make sure the little door stops so you can get back in. What'd you get? 7.2 meters, sounds familiar. Again, you could have solved for the vertical displacement with the third equation. You should get the same thing. Okay. Other than the using the wrong multiplier that Ms. Earhart did, any questions on A, B, C? Because we're going to make a change, non-symmetrical in part D. All right. D, if the ball barely cleared the 3-meter tall goalpost, how far away were the goalposts from where the ball was kicked? How far away are the goalposts from where the ball was kicked? What are we solving for here? What's the unknown? The range. And so we're looking for this range. So it's not going to be symmetrical. Here's kind of your new picture. We've got that football. It's still going to go up. And yeah, maybe it still hits the ground, but maybe there's a goalpost somewhere in here, right? And we know the goalpost is 3 meters high, and it's just barely going to just skim that post, right? So in other words, as it passes over the goalpost for the ball, its final vertical position is going to be that 3 meters. So that's why they talked about barely clearing, okay? And we're looking for this horizontal distance. So I can't just say, oh, I know the velocity, I know the time, because chances are the time is going to be less, right? So when you kick it over, it usually looks like this picture. And so we're still going to use the same velocity. There's no mention of them kicking it any differently in terms of kick angle or kick speed. And so we'll say it's the same VI and theta. And so the horizontal, that's that 0.87. Vx is that 0.87 times VI. Well, now we know that the hypotenuse was 24. So what's 0.87 times 24? $20.88. So 20.88 is going to be that horizontal. So notice to find the range, I need the time. Well, the time is going to be less than 24, but don't start doing any kind of proportion. We need to solve for it. And so pause in the horizontal, solve for time in the vertical. So just moral of the story, it's not symmetrical, nothing zeroes out. So you could do quadratic, or the quick workaround is to solve for VFY first. And it's not going to be equal to the initial vertical component because it's not symmetrical now. And so VFY squared equals VIY squared plus 2 times AY times delta Y. And so we do kick it up. So earlier we found the vertical component. And so VIY was that 0.5 times VI, which was 24. So half of 24 again is 12 squared plus 2 times negative 10 vertical acceleration. And then we've got that +3 is going to be your vertical component or vertical displacement. And so that would be minus what, 60? 144 minus 60. But then you got to take square root. And so let me know, after you take square root of 84, what do we get? There we go, 9.16. And do you think it's going to be the positive value or the negative value as it passes over the goalpost? Negative, okay? And again, that makes a difference when then we use, so step 2, work around from quadratic, we use that first equation. To solve for time. And so negative 9.16 equals that positive 12 plus negative 10 times time. So this is the time to the goalpost. It's not a total time back to the ground. It's not time up. It's time to the goalpost. And so negative 9.16 minus 12, so we're adding those two negatives, and then divide by 10, what do we get for the time? 2.11, and notice that's less than 2.4, so that makes sense, right? Okay, so now we know 2.11 seconds in the vertical, that's going to be equal in the horizontal. So bring that back up. So our range will equal that 20.88 times 2.11. And so earlier, remember, we said that the full range, I think, was 50 meters. So it should be a number less than 50. Okay, what do we get? Good, so I'm just going to call it 44 meters. And then that's less than 50. Hopefully the storytelling makes sense, right? Okay, so it started out symmetrical, then it not was symmetrical. And so we don't have time today to do page 16, okay? But pre-lab, so we only have about 5-ish minutes left. Let me go in and kind of set up lab for next time.